On to example 4. So for the function, negative 3x to the 2/3 is defined from -1 to 1 inclusive. We're going to find the absolute max and min values, graph it, and then identify the absolute extrema on the graph. Let me go ahead and just graph this first for real quick so we can get a good look at this. Okay. We're graphing from -1 to 1. Okay, if I plug in -1, that's basically saying the cube root of -1, which is -1 squared, is +1, and that would be then down at -3. If we plug in 0, it's still 0. If we plug in +1, then we get the cube root of 1, then squared is 1 times -3 is -3. Okay, and obviously this is not linear, so we probably have a curve coming up and a curve coming down. And that would be that's what the graph would look like. There's no way it's going to go undefined anywhere in that interval. Okay, so if we look at this, then we have a potential. We have an absolute max of 0 at x equals 0, and then we have an absolute min of -3 at x equals both plus or minus 1. So we can label this one right here the absolute max and the absolute min right there and the absolute min right there. Okay. And another way you can kind of look at seeing if there would be a potential is if you look at the derivative. Okay. So if I take the derivative of my function, it would be -3 times 2/3 x to the -1/3. So cleaning this up, it would be a -2x to the -1/3. Well, remember, we have potential extrema when your derivative equals 0. So if I take -2x to the -1/3 and I set it equal to 0, the only way it could equal 0 is when x equals 0. And look, at x equals 0, we did find one of our we found one of our extrema. In this case, it happened to be an absolute max. So here in example 5, for our function secant of x, we want to find the absolute max and min values, and again, all the same thing. Okay, so let's draw ourselves a picture. We're going to go on the interval from -π/3 to π/6. So let's make this π/6, π/3, and then we'll call that -π/6 and -π/3. Go 1 and 2. -1. Okay, so the secant value at 0, so it's 1 over the cosine of 0, which is 1. Here at π/6, our far right side of our interval, it's basically saying 1 over the x value at π/6, which is the square root of 3 over 2. So if we swap that around, 2 divided by the square root of 3, we roughly get a value of about 1.2. So I'll put a dot right there. Okay, and then -π/3, if we go to the far other endpoint, it's 1 over the x value at -π/3, which is a half. So switching that around, we get 2. Okay, so my graph is a curve coming down just like that, just going from here to here. Okay. All right, so now we want to answer the questions of what are my local maxes and local mins, or my absolute maxes and mins. So we have an absolute max of 2 at x equals -π/3. And we have an absolute minimum value of 1 at x equals 0. And if we wanted to kind of look at the derivative like I did before, the derivative of our function of secant x is secant x tangent x. And if we set that equal to 0, so in other words, we have two options. Since it's factored, we can say secant x equals 0 or tangent x equals 0. Well, the only time that secant is going to equal 0 is at π/2 or -π/2, and that's not in our interval. So we shouldn't be getting any maxes or minimums from there. Now tangent of x only equals 0 when sine is equal to 0, and sine's equal to 0 on that interval when x equals 0. And there you go. So that's telling us we have a potential value for a max or min there, and we actually did find one. It was a min value. Okay. Example 6. We want to find the absolute max and min values and where they are assumed to be for this function. And what I would do is just kind of like what we've been doing in the past is let's start looking at a graph for this, and especially since we have an interval on what we're going to be looking at. Okay, so -1 to 8. X to the 5/3, you know that's just the cube root of x, then all of that to the 5th. Okay, so if we plug in -1, the cube root of -1 is -1, and -1 to the 5th is -1. If I plug in 0, we'll get 0. If I plug in +1, we'll get 1. And the next number I can take the cube root of actually is 8. The cube root of 8 is 2, and 2 to the 5th is 32. So let's put a dot way up here. We'll just say that's 32. So the graph is going to be rising all the way up to there. Okay. So the absolute max and the absolute mins. We have an absolute max of 32 at x equals 8, and then we have an absolute min of, let's see, that y value there is -1 at x equals -1. Okay, and if we want to, we can look at maybe finding the derivative and see if anything would come out from there. The derivative of the function is going to be 5/3 x to the 2/3. And if we set that equal to 0, then what it's saying is potentially at x equals 0, we would find an extrema. In this case, it's not going to be a max or a min. It would have been a local one at that point. But we don't have one, so we're just going to keep going on. So our two answers were those two right there. Okay. Last example. We want to find the critical points, the domain endpoints, and the extreme values for these two functions. Well, in part A of this example, what I first want to look at is the whole part of the whole fact of asking us for the domain. Normally, if it was just y equals x squared, our domain would be all real numbers. But because of this whole radical part in here, our domain's been limited. So remember, you can only take a square root of positive numbers. And so, just our normal rules, it says 3 minus x, whatever's under the radical has to be greater than or equal to 0. So this is saying 3 is greater than or equal to x, or in our sense, our domain is anything from -infinity up to 3, and we can actually include 3. Okay, so when we're looking for possible extreme values, then at most, we could possibly get one is up to 3, so anywhere from -infinity up to 3. Okay, what I want you guys to do for 2 seconds is just pause the video, pull out your calculators, and graph this in your calculator. And then meanwhile, I'm going to draw this on here. I'm going to draw what I see, and then we're going to go from there to find it, okay? Okay, well, hopefully y'all have gotten a chance to pull out your calculators real quick and put this graph in. And I just kind of use the table function just to help find some key points. Like there's a point -1, 2, 0, 0. It goes through the point 2, 4. And then, of course, it's at 3, 0, because that's the very last far end point of our domain. Okay? And then I noticed that in order for us to get all the extreme values, whether they were local or absolute, that there was a hump right here, and I wanted to get the actual value of that hump. So when I just asked the calculator to tell me about the maximum value there, then it got the coordinate roughly 2.4 and then 4.5. Okay, so now let's start about answering the questions. So to answer the questions, let's start labeling them out. We have basically our critical points or our endpoints. Let's say this. We have an absolute minimum of 0 at x equals 0. And then we have also one of 0 at x equals 3. Now as far as absolute maxes, because this left side of the graph keeps going up for never, 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 we don't know about an absolute max. but we do have a local max because it's just any time we have a high point, a high hump. Okay, so it's going to be a local max of 4.5 at x equals 2.4. And by the way, if we want to kind of talk just some technicalities as far as what's happening with the derivative, at x equals 0, which is right in here, that the derivative, let's say, we'll say y prime equals 0. At x equals 3, though, because we're at an endpoint, the y prime is undefined. And then at the local max, which is this high of this hump, the graph is almost going horizontal for just a split second. So right there, the derivative would equal 0. Okay, so just some kind of other key topics to think about connecting everything together. All right, let's do this exact same thing for this piecewise function. If we notice, first of all, if we look at just the domain and we want to analyze it, the domain, the top portion says for all x values less than 0, not inclusive. And then the second portion says for all x values greater than 0, inclusive. So it looks like our domain is going to be all real numbers, or, negative infinity to positive infinity. So we can include everything. Don't have to worry about much there. So let's go in and let's start looking at graphing our graph. I don't know if we want to maybe do this by hand, or if y'all want to put it into your calculators. If you want to pause it real quick, put it in your calculators, and let's come back and analyze and compare what we've got. Alright, well, coming back, hopefully y'all got pretty much a similar graph to this one. Just two piecewise functions connected together. One's linear, one's a quadratic in nature, so it's a upside down parabola and then part of a line. So if we want to answer questions as far as absolute maxes and mins, well, because one part is going to keep us going forever and ever up, and one part's going to keep us forever and ever down, we really don't have absolute maxes and mins. So now what we're going to look for is a local min or a local max. Well, obviously this is the top of a hump right there, so we can say a local max of, and that y value there is 4 at x equals 1. And then for the local min, if we look to our graph real quick, it's going to be where basically our graph is undefined, or where our derivative is undefined. So it's going to be a local min of 3 at x equals 0. All right, and this wraps up this section.